All right, so it is my pleasure to moderate our paired research talk session today. Before we get officially started with our session, I have a little embarrassing thing to do to Donna. So let's see if I got this right. Excellent. So Donna Llewellyn, the woman who welcomed you today, will be retiring at the end of 2024, and this is her last ICUR. So can we get a round of applause for Donna Llewellyn? You're welcome, Donna. Yeah, Donna did not know this was happening. At any rate, at our annual Spring Undergraduate Research Showcase, we launched a new fund for undergraduate research at Boise State in her honor. And we wanted to just let you know that such a fund exists. For those of you who are Boise State, it'll help support your own research. For those of you who are from across our state or visiting our state, it's just a nice opportunity to know that there are things and there are funds that support undergraduate research. I did put a QR code on here in case you are interested in supporting the fund. But this was the office, the Institute for Inclusive and Transformative Scholarship, IFITS. The staff really wanted to honor Donna's dedication to undergraduate research over the last decade, and really the transformation that undergraduate research has undertaken at Boise State with Donna's leadership. And so we are grateful for your leadership and all of the work that you've done, and thank you. With that, let me tell you a little bit about paired research talks and what they are and why we have them. So on stage with me, I have faculty and students from the three sponsoring universities. First, we have Idaho State University, University of Idaho, and Boise State University. And each one of the teams will provide you with a little bit of an insight into what their work looks like with the faculty mentors, sort of setting the stage and setting up the larger research question, and the undergraduate students sharing their own experience and sharing the specific project that they're working on currently or that they've recently worked on. Without further ado, I'd like to introduce our pair from Idaho State University. We have Brinley Adams and Leslie Nickerson, and let's welcome them with a round of applause.
Hi, everybody. I'm Leslie Nickerson. I'm an assistant professor at ISU. I'm going to be talking a little bit about one of the projects that I've been working on with my student, Brinley Adams. So we're kind of an organic lab, an organic methodology lab, which really just means that we're looking at developing new methods of making bonds or making particular functional groups. So we're going to talk a little bit about how we've been adapting that to be a bit more sustainable. So a little bit about me first. I'm actually an Idaho kid. I was born in Boise, Idaho, but lived most of my life in Middleton, Idaho. So if there's any Middleton kids out there, yeah. I did my Bachelor of Science at U of I, and then I did my first foray outside of Idaho and went to California for my graduate studies at UC Davis. I was lucky enough to be able to do a little bit of a visiting graduate student thing in Michigan, so I lived in Michigan for a summer, and then went to Massachusetts for a postdoc, and so I kind of went all over the country, but then ended up back in Idaho for my assistant professor job at ISU. And I'm going to pass over to Brinley.
Hello, I am from Preston, Idaho. I'm currently a senior at Idaho State. I'm majoring in chemistry. I'm planning on graduating spring of 2025. A little bit about how I got into research is I also work in the chemistry stockroom, so I've had some experience doing distillations and other lab work, but I wanted to do more hands-on research because I had an interest in that. I also have an interest in organic synthesis. I really enjoyed synthesizing materials in my organic chemistry labs and my classes and stuff. So between the working in the stockroom and the organic lab work I did, I wanted to do more research. So some future goals of mine is I would like to go to grad school to get my PhD in organic chemistry.
So most of what my lab focuses on is green chemistry, which if you have not heard of it, it's really making chemistry more sustainable. So I just wanted to share this quote just before we get started here. So without the innovations of chemistry, sustainable development will be impossible to achieve. If the chemistry that humans use to pursue these innovations continues to be itself unsustainable, sustainable development will be equally impossible. And that was from Anastas and Zimmerman, who are kind of the fathers of green chemistry, or the sustainability idea. And that's kind of the motto of what our group is focusing on, and making sure that the chemistry that we're using to make all of these highly functional products or highly valuable products is sustainable, so that we can continue that path of sustainability. Okay, come on. There we go. So the principles of green chemistry, there are 12 of them. It's very, very difficult to get all 12 in a single research project. So there's some that we focus on and some that don't really get hit. But ones that we're kind of looking at here, we're looking at a lot of waste prevention, so we're not building up a bunch of waste in our waste stream. We're trying to design things that are less hazardous in both the synthesis and the stuff that we're using. We're using catalysts instead of large quantities of materials, and trying to make sure that the catalysts that we do use are renewable, recyclable, and the solvents that we're using are more friendly for the environment, more friendly to use for the user. So that's kind of what we're looking at in terms of how we're adapting that classic organic chemistry, which tends to have a lot of halogenated solvents, it's got a lot of corrosives, it's got a lot of stuff that is not very great for people or the environment. Oh, so that, I don't know why that's showing up right now. We'll just, hopefully, okay. So for my group, this is kind of a little bit of an overview, so in case you want to talk to me about it later. Most of it is focused on green chemistry. I do have one little pedagogy project that I'm working on in developing a learning assistant program in my organic chemistry class. We do a little bit of chemical biology that's looking at kind of the green chemistry ways of looking at fluorescent tagging on tRNA, so being able to analyze what tRNA is doing. Instead of using radio labeling, we're using a fluorophore that we've installed synthetically. We also have a project on mycelium, which if you don't know what a mycelium is, it's just a mushroom just before it's actually in the fruit stage of the mushroom that degrades plastic, so we're looking at the analysis of that. And then most of what our project does is in this heterogeneous catalysis field, which is looking at kind of those classic organic chemistry reactions and finding other more sustainable ways to affect those. So the one we're going to be focusing on today is the Prince-Pinnacle rearrangement. That is going to be the project that Brynley is going to discuss. So we first need to talk about what the Prince-Pinnacle reaction is. So in case you are not familiar with organic chemistry, you don't really need to be hopefully to get through this talk. So if you focus in on the red and the blue spheres here, you can see that they are basically connected at the start of the reaction on the left-hand side of the arrow, and then on the right-hand side of the arrow, they are disconnected. Okay, so there was some kind of rearrangement that occurred here to affect that change. This was originally developed in 1969 by a French chemist, Mousset. He published in a French journal. We had to translate them. It was a whole ordeal. But he actually used a heterogeneous catalyst when he first developed this. So that's montmorillonite K10. It is just a type of clay. So he basically threw dirt into this reaction and then stirred it up. I was like, oh, look at what we made. And he was not expecting this. This was something that he just found. And it didn't really go anywhere past that. And then in the 80s, Larry Overman, who's a pretty famous organic chemist, he came and found basically the same thing. He used a slightly different starting material. So he used an acetal, which Brynley's going to talk about a little bit later. But again, we have those same kind of red and blue spheres. They start off connected, they end up apart. You're making the same kind of product at the end. So for the organic chemists in the audience, this is really for them right here. But I wanted to include this just because I think if we're talking about undergraduate research, it's really important to think about how the undergraduates actually approach the research question. So this project was specifically tailored with that in mind to make sure that we're using a lot of components and ideas that come about in sophomore organic chemistry. So we're looking at acetal type chemistry and carbocation rearrangements, both of which are covered in the normal year-long sequence of organic chemistry. So we won't go into a ton of that, but just so that we kind of know how things were put together. Okay, so Overman's Prince-Pinnacle reaction had a lot of good things about it. He did a ton of work, so he has a really wide breadth of work that he has in terms of what kinds of substrates he can do, the stereoselectivity and the stereochemical models that he developed. But there's definitely things that could be improved from it. So right now he's using dichloromethane as a solvent. In case you aren't up with like all the EPA regulations happening right now, dichloromethane is getting pretty heavily regulated here in the next little bit. So it's going to become a lot harder for academic research labs to be able to use it. So that is something that needs to be fixed. Uses a lot of corrosive catalysts, so tin tetrachloride, boron trifluoride. All those things are going to end up in some kind of water extraction afterwards, so you're creating metal and halogen waste. And they were all done at pretty cold temperatures. -78 is a pretty hard temperature to achieve, especially on a larger scale. So there's definitely things that could have been improved over this reaction. You guys like double click. Okay, so heterogeneous catalysts, just in case you need a little bit of a refresher, this is a heterogeneous mixture that is shown up here in this picture. It's a picture taken by my dad, thank you. So in this, it's just water and gravel. Okay, so that is a heterogeneous mixture where you've got two components of different phases in it. So one is a solid, one is a liquid, and that's exactly what we have going on in our reaction, where we've got the solid catalyst, and then all of the other components are dissolved in the liquid. So the nice thing is, if you imagined and I asked you, I want just the gravel and not the water, you could just pour that through a filter and be like, here's your gravel. And that's exactly what we can do with the catalyst. So it's really easily recoverable, and it's not something where you're going to have to do a lot to get it back into its normal state. Generally, you can just kind of heat it back up, and that catalyst is returned back to an active state. And then we don't have any aqueous waste created because we can just filter it off and then remove our organic solvent, and we're done. So zeolites are going to be the kind of main catalyst that we've been using. They're just aluminosilicates, which if you've ever been walking around outside, you've probably walked on these, you've probably scraped your knee on these. They're very, very common. The zeolites that we tend to use are usually not naturally derived, just because those zeolites tend not to be very pure. So we use synthetic ones, but it is the same kind of things that you find in a lot of minerals that are just lying outside. They have different pore sizes. You can see the structure. It's got kind of these pores and channels, and that's where reactions can take place within those active sites on those pores and channels and on the surface. We can modify these. We're kind of in the very, very beginning stages of this, so most of what we've done has been with commercial zeolites, which I think makes a stronger, more meaningful method anyways, just to make sure that we can go, oh yeah, this is so easy to do. You take it right out of the bottle. So to get there, we really have to make the substrates, because what I've talked about with the Prince-Pinnacle reaction and all that is like 3 steps in. So I'm going to pass over to Brynley, and she's going to talk about what she's actually done here for this process.
Okay, so most of my time spent in the lab is making our starting material, the acetal, which is colored blue, as you can see on the screen. We start with our starting material called acetoin, and we react it with 2 equivalents of a Grignard to make a diol, which is colored red. We get about a 55% yield when we do that. It is a very tricky, challenging step. I have had a lot of personal issues with it myself that I'll go into more detail later, but it's because it has to be run in air-free conditions, can't have any water around. It has low yields, it's very difficult to purify, very problematic. The next step is we react the diol with an acid catalyst, paratoluene sulfonic acid, and with 1 or 2 possible types of aldehydes to make 2 different types of acetals. So we can react it with a less bulky aldehyde to make the acetal on the top that you see there, and we can react it with a more bulky aldehyde to make it the more bulkier acetal shown on the bottom. So as I mentioned, forming the diol with the Grignard is the trickiest step. I have had a lot of issues. So when I first started doing it, I followed, Okay, well, that's supposed to say followed the procedure, so the text is gone. Anyway, sorry guys, but I followed the typical procedure and I got a 2% yield. It was awful. So then I decided, well, maybe I need to adjust how I'm purifying it, because we had been originally purifying it using a Kugelrohr, which is the equipment you can see in the picture there. So I decided to adjust the temperature, the time I was purifying it for, so I purified it for only 30 minutes instead of 2 hours, and I got a 15% yield. And so that was not that much better. So I decided to adjust the temperature I was purifying it at, and I got a 0% yield. So from there, I had to read a bunch of literature, do a bunch of problem solving. I decided to skip the purification step entirely because that's where most of my product was going, but I also decided to improve the workup by doing a brine. And anyway, that's supposed to that is supposed to say 56% yield. Anyway, it was a success. It was a lot of failure in figuring it out. But just to clarify, yield is the amount of product you obtain in comparison to the amount of material that you started with. So the higher the yield, the better. So 56% yield is obviously significantly better than a 2%, 15, or a 0. So does zeolite catalyze the Prince-Pinnacle reaction? Yes, it does. So this is the actual step we are actually studying for our reaction. So we start with the acetal, colored in blue there, and we react it with a heterogeneous catalyst, usually zeolite, and then we make our tetrahydrofuran ring, shown on the far right. For the two different possible rings we can form, the less bulky one on the top, we get an 81% conversion, and then for the more bulkier one on the bottom, we get a 91% conversion. Conversion is different from yield. We quantify this reaction in conversions instead of yields. Conversion is the amount of product the amount of starting material that was converted into the product. It's not the actual amount you made itself. And we find these conversions using hydrogen NMR. So we take an NMR like this one, and we zoom in on a region where we can find both starting material peaks and product peaks and analyze them. To just kind of, for those of you that aren't organic chemists and aren't familiar with NMR, a good way to describe NMR is it's like taking an MRI of a molecule. So we zoom in on this location here, and we find the starting material peaks, which can be seen in the NMR on the top, and then in the NMR on the bottom, you can see that those peaks of the starting material, the acetal, are gone, and instead there's peaks present that indicate that our product was formed. So in this case, because there's so little of our starting material present in the bottom NMR, and there's a lot of peaks indicating that our product formed, that means we got a very good high percent conversion for this reaction. So far, we have tested a lot of heterogeneous catalysts. Most of them have been zeolites, which are covered in the blue segment there, but we have tested one other heterogeneous catalyst that is not a zeolite, which is montemorolite K10. We've gotten the best results with beta ammonium, but we've also had decent results recently with Y hydrogen and beta hydrogen and a few others. We don't get as good results with some of the other ones shown on the far right of the graph, as you can see, but more reactions could be run to see if we could try to improve those conversions. I personally myself have done a ton of solvent screening because previous work on this project used dichloromethane as a solvent, which is carcinogenic, so we are trying not to use that. So we've been trying to see what solvent would be better to run this in. So I've tested all of these solvents shown here, and the most effective one has been ethyl acetate and toluene. So some of our future work, we're hoping to eventually expand the substrate scope. So far we've only done an ethyl group and isopropyl group, so both are, isopropyl was the bulkier one, ethyl was the less bulkier one. But we're hoping to try other bulky groups too, like possibly a ring or a double bond, something like that. We also would like to do more work with a flow reactor. Flow reactor would be, it's a good thing to continue working on because it has industrial applications that would be really helpful. So what a flow reactor even is you take your starting material, the acetal, and you dissolve it in solvent, usually ethyl acetate, and you pump it through a packed bed full of zeolite under pressure, and that will convert it into your product. So we'd like to continue doing more work with that, especially since it has industrial applications. So I've learned many lessons while working in the research lab. I have learned how important scientific communication is. It's important to be communicating with your PI about the progress of your project, but it's also important to communicate with your lab mates so you're not like stepping on each other's toes. But it's also important to learn how to give presentations like these or give poster presentations and be able to communicate your scientific research in a way that makes sense. I've also been able to further develop my chemistry lab skills and my problem-solving skills. Before working in the research lab, I was not very familiar with how to purify things, so I now know how to run a flash column, for those of you that know what that is. I also know how to run reactions under air-free conditions, things like that. I've also have learned how to develop a plan to move forward after failing or experiencing a setback, especially with the Grignard reaction that I talked about. I failed at that so many times, and I had to learn to not let failure bog me down and how to pick myself back up and try again and think through what could have gone wrong so I could move forward. I also have had a lot of experience stepping out of my comfort zone, and it's helped me to grow and improve as a person. Talking in front of people is not my strong suit, so this is a good experience for me. But anyway, I'm going to turn it back over to Dr. Nickerson.
So a few things that I've learned, I'm finishing up my third year, I'm just starting my fourth year at ICU, so I feel like I've been going through this big learning curve with my students at the same time. So a few things that I've kind of picked up in my time as an assistant professor is to really get the whole story first. I definitely made mistakes at the beginning where I would look at something, somebody would ask me something and I would just go with the first answer that popped into my head without getting the whole story. And so now I've learned that you have to ask a lot more questions for each question that you get asked. If I was looking at myself when I started, I would tell myself to just calm down and that mentoring is really a process. And the amount of kind of professional development and enrichment that I've given my students in my research lab has definitely increased over time and something that doesn't have to start exactly where you see it as a graduate student in a developed group. I've also seen that students can help train each other, and that really increases confidence and deepens their understanding. But this requires pretty frequent check-ins just to make sure it doesn't turn into a game of telephone, because I've definitely seen that happen as well, where it's like, why are you doing it that way? Like, oh, so-and-so told me to do that. So that's definitely something to watch out for. But I think probably the most exciting thing that I've been able to see is just how my students go just take things and run with it and really go above and beyond my expectations if they're kind of given that freedom to start directing that research themselves. So with that, I'd like to thank my whole group. So this is them pictured here. Everybody that's bold is somebody that worked on this project, either that are in the group right now or graduate students down below. Also like to thank all of our funding sources, including the State Board of Education and most recently the National Science Foundation. So we're happy to answer any questions during the panel portion, and thank you all for listening.
Thank you so much, and my apologies about the blank squares, but good job on knowing your numbers, Brinley. To follow up on Donna's tips for attending conferences, I'd like to offer this unsolicited advice. For those of you who are attending a conference for the first time, this is a learning experience, right? And learning happens best when you reflect on what you're learning. And so in whatever way it helps you, if it's just taking a mental snapshot or taking a picture of a slide or writing something down, take notes, try to process what you're hearing. As you're listening to the students present about their experiences, I want you to think about the things that you have in common with them and the differences that you have in your experiences, and really just sort of sit with that and think about your research experience. We don't really get time to sit and reflect about our research experience. And so we hope that you take the time in the next couple of days to really just sit with it and think about what you're learning. Our keynote speaker also mentioned that the things that you're learning and doing research are not just the particular skills that you're picking up, but also life skills. So just think about that, reflect on it, take notes on it, and as was mentioned already, after the talks, the 3 presentations, we'll have time for Q&A. So if you have questions, write them down so you don't forget them, and think about questions to ask afterwards. So without further ado, I'd like to present our second pair from University of Idaho. We have Lizzie Wilcoxon and Ray von Wondrushka. Did I get it? Okay, excellent. So let's go on. The computer is in that room, so if you point that at this thing,
All right. All I'm going to tell you about myself is that my name is Ray von Wondrushka. I think I talk loud enough. I don't need this thing, but my name is Ray von Wondrushka. I'm a professor of chemistry at the University of Idaho, and I've been there for 36 years. The last 18 years of which I've been chair. As a matter of fact, I was chair when Leslie herself was an undergraduate researcher at the University of Idaho, and. Well, Lizzie, my student here, will introduce herself when it's her turn. Okay, now, what I'm going to tell you about, what we are going to tell you about is not what you would call cutting-edge research. It's applied research, okay? And it has a very strong educational component. So, it's the analytical chemistry of historical archaeology. What we do, so we meld the 2 fields, right? And what we do is we get from all across North America, we get archaeological artifacts, materials, from museums, from other universities, from state agencies, all from archaeologists. And it's historical archaeology, not prehistorical. And they've found stuff that they don't know what it is. And they send it to us to chemically analyze it. What is this is the question we always have to answer. So, where does it come from? Well, this thing is never up to date. The thing is, it comes from everywhere. As far away as the Virgin Islands, up in Canada, along the East Coast, south, the West Coast, everywhere. All roads lead to Moscow. Okay, so let's just say a word about what the project's about. I mean, I've done chemistry, I've done electrochemistry, I've done surface chemistry, I've done soil chemistry. This is just a fun project that we've been doing since 2008, and we've had a lot of students in it. It's continuing, it never stops. So the thing is this, what do we do? It's a continuing undergrad research program. Student motivation tends to be high. Okay, students like to do this. Okay, it's chemical detective work. What is this? Okay, and there's these eureka moments. Yes, I got it. Often enough, it's also, oh, there's just dirt in this bottle, but and oops, and then it's an educational vehicle, of course. It's not recipe-driven. Many different techniques are used and learned by the students. The results are real. It's real stuff, okay? And lots of independent thought goes into it. Interdisciplinarity is self-explanatory. I mean, we have chemistry, we have archaeology, we have history, we have anthropology. They all have to look at all these aspects of an artifact to figure out what it is. Okay, now, of course, it's data to archaeologists. You know, we get a lot of feedback, requests from other institutions. The word spreads. I mean, we've been doing this for, 16 years now. And there's publications and presentations such as, well, this one. Okay, so what are these artifacts? Well, we've done hundreds of them, literally hundreds. And it's all kind of stuff, coins, bottles with stuff in it, shards with stuff stuck to it, a bone, a pile of wood, something you have no idea what it is, and we never know what we're going to get, okay? The question the archaeologists ask us, what is this? And that's where we go after it. We have to figure out what to do and how to do it. Then we write a report. They include our report in their reports for their projects. So, okay, techniques. Oh man, there are way too many to list, but I picked out a few, that are important. Okay, first it's the observation, microscopes, just looking at it, what does it look like? Stick it in a high temperature furnace, see what burns off. Infrared spectroscopy, always very important. Look at the functional groups of the materials that we have. Atomic absorption spectroscopy, just a simple little flame AA spectrometer, tell us about the metallic content of the sample that it might have. We also do flame photometry, but just for alkaline earth metals. For a wide scope of metallic content, we use inductively coupled plasma spectroscopy, ICP. And of course, very important for organic materials is GCMS, gas chromatography mass spectrometry. Sometimes we do the liquid chromatography equivalent of it, HPLC-MS. And every once in a while, we do scanning electron microscopy with a energy dispersive spectrometer attached, so we can look at all the elemental content of our sample. And then, of course, there's the old spot tests. Fritz Feigl, many years ago, wrote 2 books, Organic and Inorganic Spot Tests. There's a spot test for everything, okay, and we do them all the time. Okay, now what I'm going to do, just very briefly, I'm going to mention, I picked out 2 things here, 2 little examples of the kind of thing we got and the kind of thing we worked out. So here's a sample we got from Stanford University from Barb Voss, who is a archaeology professor there. And what you can see there is a little flask. So it's a single-dose traditional Chinese medicine vial. Sometimes called an opium vial, which is nonsense because you never get an opium into the small hole here. Anyway, what it had in it was a red solid. The question was, what is that? So we looked at the infrared spectrum, had no organic content. It's not soluble in water, hydrochloric acid or hydrofluoric acid. It is soluble in aqua regia. It loses almost 92% of its weight when you put it a few hours at 800 C. It seems to evaporate in a flame. Huh. And it turns black when it's heated above 400 C. It has some iron in it and some calcium. What is it? Okay, well, it's a medicine, okay? It's red and it's solid. It's Chinese medicine. Well, the traditional Chinese medicine is very intricate. They have many minerals that they use internally often, most of the time, as for medicinal purposes. Could it have been realgar? That is used in TCM. Well, no, that has arsenic in it. There's no arsenic in it, so no, that's not it. Maybe hematite, ferric oxide. It's got a lot of iron in it. We only had a teeny bit of iron. So we did a mercury test. Darn it, there's mercury in it, a whole lot of it. So it's red, it's a solid, it's a medicine, and it has mercury in it. Most likely it's cinnabar, mercuric sulfide, which is a TCM medicine. Did a few more experiments, as a matter of fact, if you heat it above 500, it seemed to evaporate in the oven, in the furnace. It's because it decomposes, okay? It's not soluble in these solvents, but it is soluble in aqua regia. And it turns black above 400, but mercuric oxide, which is also red, also goes black above 400. But it is soluble in hydrochloric acid. Ours is not. There's only one thing left. It's cinnabar. Now, why would they use cinnabar internally as a medicine? Well, here you go. It is if you have a tummy ache, it may seem like a bad idea to take 1 gram of a mercury compound, right? Well, it is a bad idea, okay? But it's still being used in TCM. And that is because it is so poorly soluble in stomach acid, only a little bit dissolves. Just enough to kill the bugs in your stomach, not enough to kill you. So here is this is an interesting one. Here we had some coins that we got from the Kamonchang State Heritage Site. It's a museum there in John Day, Oregon. 2 coins, one side, the other side. I only talk about this first one here. And the writing on it told us that it was minted under the Emperor Kangxi here, who ruled from 1654 to 1722, so quite old. And the question was, what is that dark rim around the outside? Only on one side, not the other side. What is it? Okay, well, we analyzed the metal. It's brass, pretty simple. The dark edge is organic. Infrared spectroscopy tells us that. It looks a bit like blood, doesn't it? Congealed blood. We did a luminol test, no blood. However, our biology friends told us that it contains cells, most likely human cells. Hey, put all this together, this must be a coining coin. Now, what's a coining coin? You don't know what it is because nobody does. But in fact, what it is, you take a coin, and it's still done to this day. You scrape it along the skin. Brings up welts. Looks very painful. And why do people do this? Well, it was done since essentially forever. In China, it's done to this day because it brings the toxic elements to the surface. So be it. Here's a photograph from someone in Southeast Asia who had it done. It doesn't look very comfortable. In any case, that's my little introduction. It's the kind of work we do. And Lizzie will now tell you a little bit more about something that she has specifically done.
Alrighty. I'm Lizzie. I'm Lizzie Wilcoxon. I'm a senior studying chemistry at the University of Idaho, and I'm currently working in Ray's lab. And today I'm going to be telling you about this larger bottle we recently received from archaeologist Laura Ng out of Grinnell College in Iowa. It had this crusty orange substance along most of the interior walls, and the IR spectrum showed that it had little or no organic content in it. In a muffle furnace, it had a 15% weight loss, and it was insoluble in water, hydrochloric acid, and aqua regia. This is a bit of a problem since most of our tests require the sample to be dissolved in something. To remedy this, we fused it with a lithium carbonate and zinc oxide in a platinum crucible at very, very high heat. This then produced a mass that was soluble in hydrochloric acid. On this dissolved mass, we performed atomic absorption in inductively coupled plasma spectroscopy. This told us that it contained quite a bit of iron, magnesium, calcium, and barium, as well as some trace amounts of manganese and sodium. Following this, we did several different spot tests, and the only one that was positive was for sulfur. All the tests for nitrogen, sulfates, phosphorus, and mercury were negative. Then we found that if we heated it to greater than 150 degrees Celsius, it first turned to a very dark brick red color, probably due to the water loss in the sample. And if we heated it even further, it turned even darker and appeared almost black. The darker material, curiously enough, was soluble in hydrochloric acid and also weakly magnetic. Here you can see the brick red portion of the material, which looks almost identical to pure ferric oxide. And here you have the material after it's been cooked even longer, and it had these dark chunks, almost black, and we found that these were the magnetic portions of the material. This evidence led us to the conclusion that the bottle originally contained the orange or hydrated form of the mineral hematite or ferric oxide,
as well as some other random minerals mixed in with it. Heating it magnetized it, suggesting that a ferrimagnetic material was formed, such as ferrosulfuric oxide, which occurs naturally as magnetite, which is a black mineral. Magnetite, contains both iron 2 and iron 3 in its unit cell, but hematite contains only iron 3. So somewhere in this process, some reduction had to have been taking place. But now the question is, how could this have happened? It's been shown that hematite can be reduced by a suitable reducing agent while being heated. For instance, hydrogen gas can take some of the oxygens and produce water while converting the hematite into magnetite. Alternatively, carbon monoxide can undergo this process, where it takes an oxygen and produces carbon dioxide gas while converting the hematite into magnetite. But clearly, there was no hydrogen gas or carbon monoxide in this process in our sample, but we did find sulfur. The sulfur was likely taking some of the oxygens and producing sulfur dioxide gas while still converting the hematite into magnetite. Laura Ng also sent us this much smaller bottle, which also contained an orange solid, but it had a much finer texture, as you can see in this 50 times magnified photo. And it also had to have been in a suspension at one point, because otherwise it'd be impossible to get in and out of the narrow neck of the bottle. We performed several tests on this sample, and all of the chemical signatures, including the infrared spectrum, were identical to the previous sample. This had made us think that they both contain impure hematite. But we're still unsure as to why this one was ground to a fine powder and the other one was not. Additionally, their purpose remains a mystery, but they could have been a dye, maybe. Ray and I'd like to give a special thanks to the Carl and Kirby Dias, the University of Idaho Office of Undergraduate Research, and our archaeological guru, Mark Warner.
Got nothing more to say.
And there'll be time after the third presentation to ask questions. All right. Our third group is a quintet, not a pair, from Boise State University. I'm going to read all the names first. We have Mikhail Strix, Hayden Levy, Mac Bennett, Allison Simler-Williamson, and Stephanie Gala. That's perfect.
All right, thank you, everybody. We are a group of scholars from Boise State University, and we're really excited today to talk about a new course that we have at Boise State, which is the Art Science Integration Vertically Integrated Project. My name is Stephanie Gala. I'm an assistant professor in avian biology at Boise State, and I'm one of the co-instructors of this course. And while I'll be kicking it off today, I'm really excited to introduce our other co-presenters, including Mikhail Strix, our students, Mac Bennett, we have Hayden Levy, and Allison Simler-Williamson, who is another co-instructor of this course and an assistant professor in biology. I'm going to see if I can, yeah, okay, that's better. All right, so, to get started, we want to talk a little bit about the arts and the sciences. These are two different disciplines that help generate knowledge and understanding in our world. Because these are two different epistemologies, they're often siloed or taught very separately. But the problem with siloing is that it's naturally limiting. It demonstrates that to be a scientist or to be an artist, you have to follow a specific path or a way of thinking and being in this world, with scientists often being perceived as more cerebral and artists being perceived as more emotional. But in reality, we know that scientists have to be incredibly creative in their day-to-day lives, and artists also need to be quite experimental and pragmatic. Another problem with siloing is that it ignores the natural overlap between these two disciplines. Both of these have processes and modes of inquiry for understanding the natural world, and both build spaces for creativity, curiosity, and wonder. So a lot of people feel like at these intersections of arts and sciences is a really great place to invest and build time, because if we do, we become better communicators, we have a better chance of solving really complex challenges presented by our world today, and it also builds more spaces for people to have a better sense of belonging. And there's a lot of people here at Boise State University who value this intersection of arts and sciences. We have a lot of people who live and work at this intersection as well. And with that said, I'm excited to introduce our mentorship team for this new course. We have Megan Katu, Sarah Dalrymple, myself, and Allison Simler-Williamson. And if you looked at us on paper, of course you'd see that we're all scientists. And it might seem like maybe we're just scientists and that we've taken a very similar path. But the more you get to know us, the more that you'll also learn that we also lead rich artistic lives. A lot of us have gotten degrees in fine arts or are practicing art practitioners along the way. So as a group, we came together and we wanted to build a community that really embraces these intersections of arts and science. And as we came together, we learned that we're not alone. There were other scholars in chemistry and also scholars in the arts department who also wanted to build this community. So together, we've been building what we call the Art Sci community, which has many different mechanisms to unite these modes of inquiry. And while I'd love to talk about all of these different mechanisms, we're going to be focusing on one in particular, and that's our Art Science Integration Vertically Integrated project. And just a note to say that us coming together also led to some really wonderful funding that helps support these mechanisms along the way. So for those who are unfamiliar with a vertically integrated project or a VIP, these are courses that blur the lines between traditional lectures and hands-on scholarship. So we launched the Art Science Integration VIP in fall 2023. Our goal was to introduce these two different ways of thinking and being and seeing where they intersect and overlap. We chose a theme for this last year, and the theme was adaptations, which is pretty cool. And we had scientists that were able to visit our classroom, talk about their scholarship, how it relates to adaptations. We also had artists come and visit and talk about how their scholarship relates to our theme, and also how they see arts and sciences intersecting, if they believe that they do or not. So this provided a really great place for all of our participants to explore these two different epistemologies. Students also had the opportunity to learn different artistic techniques along the way. They had design time to create their own projects that related to this theme. And they also had dedicated making time and resources to be able to build their own products. And with that said, we're really excited to celebrate some of our students today who are going to talk a little bit more about their experiences in this vertically integrated project. And with that said, I'm excited to pass this off to Mikhail Strix, who will talk about this a little bit more.
Hi, I'm Mikhail. I'm a biology major and formerly an art major. I switched fields after I realized that I didn't want art, a major source of rejuvenation for me, to take on the pressure and obligation of a career relied upon for income. Despite this decision, or possibly because of it, art remains an important part of my life. The Art Science VIP program provided an opportunity for me to combine my two favorite things and connected me with a genuinely wonderful group of people. And I completed two whole projects. The first, mycoremediation, on the left, was created using a 3D embroidery technique called stump work, and was inspired by the existence of mushrooms that are capable of digesting plastics, and by the copious amount of red plastic mesh tangerine bags that were in my house at the time. The second, isolate number 112, is primarily felted wool and was inspired by the fungal isolates that I work with in the Simler-Williamson lab. This isolate is a part of my current research project and is also featured on my poster in tomorrow's session. How does this one work? Middle button? Side button? Side button. Okay. I want to share my main takeaways from my experience in the Art Science VIP program. The first one is take your time, but not only in the traditional sense, also as a reminder to take time away from your work. Put it on a shelf, let it breathe, and give yourself space to problem solve. Return to it when you can give it the attention it deserves, and the outcome will be better in the end. Second, embrace the unfamiliar. Try it. Do the things that intimidate you. Stump work and felting were both completely new to me. There was definitely a learning curve, but I worked through it and figured it out in the end. Change your perspective. Temper your initial reaction to something you haven't seen or experienced before. Pause and consider before passing judgment. Isolate number 112 was my first attempt to share the strikingly diverse beauty of fungi in a form meant to reduce the ick factor that often repels people. Lastly, create something unconventional. Experiment with new materials, techniques, and strategies. Replace all fabric with red plastic mesh tangerine bags. Maybe not that, but still, your best option is not always the most traditional one. As an anxious neurodivergent adolescent, I spent a lot of time looking at the ground and specifically not at other people, and I developed a special place in my heart for the tiny, often overlooked things. Fungi, lichen, and moss bring me the most joy. The best piece of advice I can offer, no matter what field you're in, is this: find the things that excite and inspire you and shape your work around them. And this is Mac, who will be speaking to you next.
Hello, I'm Mackenzie Bennett, and I actually have a background in zoology and performing arts. Oh, thank you. And this is my piece that I did for this course. This is Industrious. It is spray paint, acrylic, and craft gears on PLA plastic model. It's actually a 3D printed coyote skull meant to look like cast copper with gears replacing the major jaw muscles. The process for creating it was very interesting. I've never done anything like this before. I had to dig out my comparative anatomy lab manuals to create diagrams of where the gears were going to go, and I ended up getting help from the BSU Maker Lab to learn the basics of 3D modeling and printing. And I've actually gotten a lot more into 3D printing now as well. I've actually created a lot more skulls to use as educational models. I've always respected coyotes for their ability to thrive in urban environments, and I was inspired by the combination of industry and nature, and how humanity cannot separate itself from nature. We exist within a surrounding ecosystem, and ecosystems exist within our environments. These two things are inextricable, and I thought that it would be very interesting to illustrate a connection between them on a fundamental level, such as a skeletal structure. Thank you very much, and I'm going to hand it off to Hayden now.
Hi, my name is Hayden Levy. I am a biology student at Boise State University. My emphasis is in ecology, evolution, and behavior. And I consider myself both a scientist and an artist. I think sometimes we take for granted the creative thinking that goes into science, and vice versa. It takes the same kind of thinking to create a painting or a sculpture as it does to come up with a theory or a method of experimentation. Developing both scientific and artistic skills makes us better scientists and artists. I believed that before I joined the VIP, and I believe it even more after. Another thing I believe is that humans are not separate from the ecological world, nor do we have any ownership over it. We are simply a part of it. Creating art is how we understand the world, and throughout history, humans have used natural symbolism to show our own reflections. So this is what I made. This is a fabric collage tapestry thing. It's made of beads, glass, fabric that I found at the thrift store and lying around my house, paint, most of it expired, embroidery, everything. And what it visually is my interpretation of the tarot card, the Magician. Tarot has always used natural symbolism, things from the natural world, to represent human archetypes and situations. The Magician represents the idea as above, so below, which is that the microcosm mirrors the macrocosm. This is the idea that everything is interconnected, which is also, in my opinion, the central idea of ecology. It might not seem obvious, but the way that I made this fit the VIP theme is that I believe adaptation is the way that the world drives itself back towards balance when it is experiencing change, and that everything, which is interconnected, is working together to recreate that balance. There are so many details in this piece, and they all have specific meaning to me and my life, but I don't feel the need to explain it. I want people to find their own meaning in this piece and to see their own reflection in the water, as it were. The process was inherently collaborative and improvisational. Every single VIP lecture, guest lecture, field trip, collaborative session, all of the feedback I got from my mentors and peers was incredibly helpful. There were so many ideas for this piece that I never would have come up with on my own, and so many things that made it in that were direct ideas from my peers and my mentors. So I'm really grateful for that. I didn't have a specific endpoint or plan for my process. It's kind of like how they say beavers are never done building their dams. I feel like I could continue working on this piece or similar pieces based on this idea forever. And what I found is that science is really similar to the artistic process in that way. It is also collaborative. It is also a group effort. And it is also never finished. We can always continue expanding upon our ideas. The experience in this VIP had a positive impact on me. It was really awesome. And I feel like it made me both a better scientist and a better artist. And with that, I'm going to pass it on to Allison.
I'm Allison Simler-Williamson. I'm one of the fellow co-instructors of this course, and you just heard from a series of 3 of our students, but I wanted to highlight some of the other student work that we got the chance to see happen over the course of the year. The image on the left here is by Amina Katovic, and it's a discussion of the physiological impacts of climate change on the Arctic killifish. Sydney Smith created a series of panels to depict linkages in ecological food webs. Sandra Velasco is a PhD student researching the impacts of invasive species on South American cloud forests, and she created this diptych to show the ecosystem shifts that were occurring in her system. Morgan Callahan is an incoming PhD student who created these incredible watercolor illustrations as part of a poster to communicate the adaptations of the flammulated owl to calling in dense forests. Ava Straub highlighted the scientific contributions of Rosalind Franklin, one of the discoverers of DNA's structure. And Hannah Agren used a variety of different visual media to try to capture the feeling of being inside the visual systems of a variety of different organisms across the animal kingdom. And so one of the wonderful things about vertically integrated projects is that it really emphasizes this idea that mentorship isn't a unidirectional kind of exchange between a later career researcher and an earlier career researcher, but rather it's actually a feedback cycle and a collaboration. And so in the spirit of that, Stephanie and I both joined the students in creating our own projects over the course of the year and went through the same process of feedback and critique that the students did. You can see here that Stephanie has created these wonderful bird sculptures that actually have pliers embedded in their beaks as a way of communicating this idea that birds have evolved beaks to solve different kinds of ecological challenges and exploit different kinds of niches. Her work was inspired by her own research as well as the famous Darwin finches and the evolutionary biology work of the Rosemary and Peter Grant. And then my own project was inspired by my research in local adaptation of populations and how they're responding to ecological change. I created this suite of imaginary insects and then in a participatory art project put them out on campus and had passersby vote on their traits. And so they evolved over the course of the semester in response to people's preferences to how they looked. And so one of the things that we learned through this vertical mentorship process was really about this idea that as scientists, I think most of the time we have been trained to be mentors for folks pursuing scientific careers. And that gives this sort of illusion that our paths have been pretty linear and that we got there in a particular way. And I think one of the things that this experience opened up for all of us was to have better conversations with our students about actually how circuitous our career paths had been, and that it wasn't a single path, and that none of us are one thing. I know Hayden and Mikhail both work on research projects in my lab right now. I know Mac to be an incredible researcher of how humans relate to animals, non-human animals, and how they feel empathy. And so it was really beneficial for us, I think, to confront whether our own mentorship skills and sort of behaviors were actually lifting up not just future scientists, but future question askers or researchers more generally. The other thing that we really learned from this experience was that people were bringing so many different definitions of what meaningful art-science integration meant to them. This is a few images from our showcase that we held at the end of the year, which we put on in the Luminary and Center for Visual Arts space that highlighted all of the work that all students had been doing across the Artsy group more broadly. And people were really ranging in their definition of what art science meant to them. For some people it was effective creative science communication. For other people it was making art that embedded scientific processes or ideas or technologies. And for other people it was actually doing science about something aesthetic. And so as we proceed through this next year, this is the research question we're really pursuing is what does meaningful art-science integration look like? What are the benefits of those various definitions? And how do we make space for art in our science careers? And so we invite you to join us. We're interested in hearing from more people about what their definitions of art science and what meaningful art science integration looks like to them. This QR link will take you to the advertisement for our fall VIP course if you're interested in joining, but we also can kind of join you up with the rest of the effort. This year's theme is going to be air rather than adaptations. We'll be exploring everything from astrophysics to the migration patterns of birds. And before I close, I just want to say a quick thank you, because this really is a much, much broader effort beyond our sort of prong of it, to our funders, as well as our other Artsy collaborators, which include Lisa Hunt at the Boise State Luminary, Aaron Pierce in Art, Design, and Visual Studies, Conrad Meister and Olivier Andrusi in BSU Chemistry, Megan Catu in Human Environment Systems, and Sarah Dalrymple in BSU Biology. Thank you.
At this time, we'd like to open it up to questions. And so we have some folks that are going to be running the microphone. If possible, if you have a general question, you can address everybody on the panel. But if you have a specific question for somebody, there are nameplates in front of them. If you can read their names, you should address them by their names or address them as like the team from such and such university, all right? So just raise your hands and the microphones will come to you.
Hello, my question is in particular for the Boise State team that just presented. I'm curious because clearly all of your pieces have been incredibly moving, and even just seeing photos from the conference as a whole, with Artsy being so powerful, so beautiful, and so effective, why do you think it's been like hidden and these fields have been siloed for so long?
Go after both of them.
Oh, can you hear me? Yeah? Okay, cool. I think as humans, we like to put things in boxes. I honestly think that's why people have separated them for so long and they've been so siloed, is because we think to be a certain thing, you have to be a certain way. So I think that's why it's been hidden for so long. And I do think that there are those perceptions around what a scientist is and what an artist is that further perpetuates those boxes and how we store them. But when we take down those barriers, I think that's where the real magic happens and where we're able to think more broadly and more beautifully about our world. I don't know if anybody else wants to add to that here.
That was the most articulate way that I could have put it.
So. Oh, okay. You might need to switch.
Hello? Okay. I also think that there is a sort of I don't want to say messed up, but messed up conception of value in when we think about these disciplines. And there's this idea that scientific, more research-based endeavors have more value, more monetary value than the arts. That it's more smart, more, educated. But I think both are equally important.
I'm Brooke, and I have a question for the Art Sci VIP group. As a biology student at Boise State who is also involved in opera theater and music, I was just wondering if you guys have considered extending these VIP projects into more of the performing arts.
I can take that one, Steph. Yeah. Yes, we have. This was just our first year, and so Artsy as a kind of collective overall is really excited about making connections with all different forms of the fine arts on campus. And one of our co-instructors, Megan, is actually a really talented dancer and performer. And so I know that this last semester she did bring some of those lessons into her classroom as part of sort of the inspiration process. This fall we have invited musicians, we have invited writers, and so we're in the process of diversifying that. And if you have any input or any ideas or want to come to our class, you should email us. Thanks.
Hi, my name is Casey Wozniak, and I am a graduate student at ISU studying VIP project ownership. And I am also a avian rehabber, and I specialize in outreach education. So my question is, do you see, and how do you see this art ecology kind of 3D printing as something that we can apply to outreach and kind of hands-on activities and things like that, that can make it more sustainable rather than using previously live specimens?
Thank you very much. Yeah, I think that using 3D models and 3D printing to create at least somewhat accurate educational models of skulls, skeletal systems, other things like that, I think that that is a potentially really great avenue to go down. The way that I did my project was the model of the coyote skull that I used was actually a 3D scan of a specimen from the Smithsonian that was then put up on Thingiverse, which is a website containing free-to-use 3D models that can be printed. They're just uploaded by different institutions, different independent creators. And I did end up printing a bunch of skulls. You probably saw the picture that I used for a different final project for another class that I was in that involved educational outreach at the Birds of Prey Center here in Boise. And I thought that it was particularly effective, since obviously it's a lot more economic than getting things like plaster casts, bone clones, and obviously you don't have to deal with the sourcing of specimens, making sure that it's ethical and that all of the paperwork is done correctly. I think that that is a very good avenue to go down. The only issue would be that not all of the 3D scans are super detailed and super accurate, but yeah, I think it's a great idea.
Hi, my question is for the University of Idaho group, the chemistry and archaeology. I was wondering if you guys have taken any courses or done any research in history or anthropology to help you in your research, or if you feel that's important.
Have you or haven't you?
I did in high school.
She did in high school. No, in fact, AP. AP? Oh my God. Good for you. No, the thing being, of course, the primary requirement is for people to be able to work in a lab. And so I don't take students who I've occasionally, if they talk me into it and they're able to do it, taken freshmen, but I will take people that are maybe juniors and seniors mostly. And occasionally I've had students coming to my lab who were actually anthropology majors, but who had by chance done some chemistry courses, gone through to OChem 2, and I gladly take them. I mean, really, it would be a preference, but there are not that many of them around.
Same group, the history and the chemistry and archaeology group, but I was kind of just more curious, what's been like your guys' favorite artifact to like analyze, or like has there been like any like really special things that you've been able to see or take a look at?
Oh yeah. Let me give you a few examples, okay? We have analyzed the oldest condom in North America. Hey, I'm not kidding here. This is a fact. It came out of Maryland, 1730. And our task was to determine whether it was made of fish bladder, sheep gut, or pig intestine. For the rest, you know that. Interesting. Okay, we got a sample. We got a bottle, a beautiful bottle, out of the Burke Museum in Seattle. It had whiskey on it, okay? It was from about 1850, nicely embossed whiskey. Nice bottle. It had a little bit of a goldy colored liquid in it. Some of you may see coming what it was, right? It wasn't whiskey. Somebody had peed in the bottle. I mean, these things are precious, okay? We've done more than 500 samples. And, you know, good things do come up. You say, yes, look at that. Even, I mean, Lizzie having found that you could actually convert by heat and some reducing agent hematite to magnetite is remarkable, at least in my mind.
This is a question for Leslie and Brinley. So I know ISU Chemistry has a strong culture of undergraduate research and trying to create pathways to improve access and develop that. I'm wondering if both of you could comment on what about that system works well and would encourage other groups trying to develop those same sort of support systems and pathways to foster and encourage undergraduate research.
Do you have anything? Okay. So one of the things that the chemistry department does that I think works pretty well is we have a fall research showcase, is what we call it, that we have all of the faculty, couple research students each just talk, like bring their posters, hang out in the atrium in the chemistry department building, and then there's pizza and drinks and whatever. But it just gives students a time to really start talking to professors, and I think starts breaking down some of those barriers, because I think that a lot of undergraduate students, particularly first generation that might not know kind of how things work, is they don't know how to get involved in it to begin with. So just being able to talk to people about, talk to the students about the research, talk to the professors about the research, and just start getting to know them, I think has been pretty helpful, and we've gotten quite a few students matched up with PIs from that process. So I think that's been working out pretty well. But I think that I think there's still more to be done, and just in terms of making sure that it is not opaque and that the process is as transparent as possible to make sure that we get like the widest range possible and the most diversity in terms of what our student researcher population looks like.
All right, and we have one last question.
Cool, I'm glad that I made it in. For Ray and Elizabeth, I was wondering how you go about identifying samples that are like organic and especially like have mixed organics.
Go, Lizzie, you got this.
We use GCMS.
I mean, you have to separate them first, right?
Got you. You just
look,
pray that it's in a
every
library.
sample we ever do and every answer we ever give has the word probable in it, okay? We have a lot of, CRAP. And that in fact, you got no idea because nothing is pure. You know, it's not like a regular chem lab. Everything is contaminated. You got to pick out, like she did in her little example that she gave you earlier. You know, there's a lot of ferric oxide in there, but it's not all ferric oxide. It's all kinds of stuff. Okay, just pick out the important stuff.
That's great. Well, thank you so much, and let's give everyone a round of applause. We hope that throughout your time here today and tomorrow that you do approach our wonderful scholars and researchers and ask them more questions and talk about your experience and theirs and that you learn more from one another. So thank you to our wonderful panel, and congratulations to all of you for surviving the morning session. Woo! Yes. All right.